So let's talk about thermodynamics in general. There are 4 laws of thermodynamics. And we'll start out with this. I think the fundamental question that sort of kicks off the 0th law, which I think was the 4th one they actually thought of, but considered more fundamental. If I have a typical glass thermometer sitting in the room, what does it measure? Much closer. What do you mean by its own?
Like whatever it's made of.
The temperature of the glass?
Yeah.
Not the glass, the other part.
The stuff inside it.
Yeah, the stuff inside it. I always think mercury, but I know mercury thermometers
Yeah, that's what I was gonna say.
are rarer. It's whatever's inside it. So we have this, some sort of liquid encased in glass. I'm assuming your drawing will be much better than that. And as energy gets put into the liquid, it will expand. We've talked about that already. And so it will expand, and so there are some materials that work quite nicely for how much it will expand, considering how much energy is put into it. And that is, I haven't done the lab in a while just because it's a real nuisance, but it is one of my favorite labs where you can do this where instead of having a liquid inside the thermometer, you can have a gas inside the thermometer. So if I just take a normal soda straw and I seal off the end, and I get an air bubble in here, so I have air right here, and then water right here. Air is going to expand much more than water will under a certain temperature, so you take this and you can put it in various objects and just mark off on the straw how big the air column is depending upon a certain temperature. Now, done well, you will be able to, it'll be some linear progression, and then you can start measuring temperatures with it. The downside is it's so easy to mess up. If you do it really well, I've seen it done in 15 minutes, and I've seen it students still struggling after 2 hours. It's that kind of lab. Either you hit it right or you're just experiencing one frustration after another. Matter of fact, with that, since you can do a couple different temperatures here, body temperature, air temperature, ice, boiling water, you get easily four different temperature spots. Then working backwards, you can actually predict what absolute zero is doing this. Figuring at absolute zero, that the volume of this would be so close to zero that we'll just pretend it is zero. However, back to the 0th law. So what a thermometer measures is really just the temperature of the liquid here. Now you assume that the liquid is the same temperature as the glass. You assume that the glass is the same temperature as the air surrounding the glass. You assume the air surrounding the glass is the same temperature as the air just past that, and so on. And so that way, indirectly, we measure the room temperature, but we make certain assumptions. Well, the 0th law is what I consider to be the transitive property of thermodynamics. So flash back to math class. What is the transitive property? I'll start you out. If A equals B, that's a reflexive property, sorry, and B equals C, there we go, then
A equals C.
yep, that's the transitive property in math, transitive property of equality. That's an equal sign there. So over here, we got to, basically, we're taking that, except we got to throw a lot more words into it because it's thermodynamics. If system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. In other words, if the liquid is in thermal equilibrium with the glass, and the glass is in thermal equilibrium with the air, then the liquid must be in equilibrium with the air. Now, what's thermal equilibrium? Inquiring minds want to know. Heat flows from hot to cold, usually. Thermal equilibrium means change in temperature is statistically zero. And I can do another definition which has 10 times more words, but that's the essence of it. Now the reason why I just didn't say zero is that it is possible. I got molecules in these two. I have molecules in the water. I have molecules in the glass. They're bouncing up against each other, and locally, it is possible for the glass to get a little bit hotter and the liquid to get a little bit cooler. But I'm just as likely for that to happen as the opposite to happen. So on the whole, there's not really a change in temperature, but locally, I could have it happen. It is possible for temperature changes to flow the opposite of what we would expect. It is a non-zero probability, although it is small. It is possible for a lake to freeze in the middle of summer. It's just the odds are against it. First law we talked about on the very first day, and this is just conservation of energy. So I have heat flowing in, I have heat flowing out, I have work being done. In essence, I start out with a certain amount of energy. My initial energy plus any amount of heat in minus any amount of energy out, which is generally symbolized by work, is equal to energy final. And I can change letters around, I can put things on other sides of the equation, but in essence, I start out with a certain amount of energy, I put something in, something comes out, I end up with a final amount. We talked about how some textbooks will have these signs opposite because of what you consider to be the system. And now we're about to get to the second law of thermodynamics, the one that I consider to be the depressing one. All right, so this one comes in many forms. So we could word it as, we can never break even. In other words, I have a system here, and I put, let's say it starts out with my initial amount of energy is 10 joules. I put 20 joules of energy into it, and now I want this system to do work. So you can treat this as, there's some kid, you feed them, they have all this energy now, and you want them to do work. Ideally, they can do 30 joules, or this object can do 30 joules of work, because it's got this 30 joules of energy. If it completely expends it all, it will do 30 joules of work. What the second law tells us is no, that it will do work, and it will just lose some. It is impossible to break even. In fact, 30 joules of energy in does not translate to being able to do 30 joules of work out. You will never break even. The perpetual motion machine says that I have a machine here which takes 25 joules to run. If perpetual motion machines were possible, this machine would produce 25 joules of energy, which you can just feed right back into itself. And so it takes 25 joules in, it uses 25 joules to make itself run, and so you have perpetual motion. This cannot happen, according to the second law of thermodynamics. Now, occasionally, I have seen in the news of someone coming up with a new perpetual motion machine, or something where you get more out than you put in, and there's always been something where that hasn't worked. Questions up to here before I give you a slightly more depressing way of looking at this. Things tend to go to disorder, which also is worded as entropy increases. So think about yourself. All the atoms in your body are not just randomly put there. Every organ is in a specific place. Now, occasionally some people are born with things in a slightly different spot, but for the most part, most humans have a brain in their head. They have a heart somewhere around here, stomach somewhere around here, intestines, legs, arms, for the most, usually. And it takes energy in order to maintain that. Imagine if you have not eaten since you were a child. I do not think you would be here. It takes energy to maintain this. If I stopped eating, in other words, stopped supplying energy to myself, if I stopped eating, then eventually I would die and I would decay, and the atoms would then just sort of bleed into the ground, or however my body is disposed of. So in order to maintain your current form, you must keep supplying it energy. Let's think about it from a particle point of view. I have a slow particle here. Let's just start it out at rest. So I have this tiny little particle at rest, and I got another particle zipping along, call this A and B. So B is at rest. What's gonna happen when A hits B? Let's make it a one-dimensional collision, just for fun.
It's gonna move it.
All right, so B is gonna suddenly start moving faster. What about A?
A will slow down.
Yes, so B will speed up and A will slow down. Now, whether A bounces back or goes in the same direction depends upon the relative masses. Well, just for the sake of this, we'll just have A go in the same direction. What happened was that they started out with very different amounts of energy, and then after the collision, their energies are much closer to each other than they were, because B speeds up and A slows down. Their energies start out very different, and then they end up roughly, or closer to the same. Given enough time, all particles will be going the same speed, or have the same amount of energy. At that point, when every particle is going has the exact same amount of energy, the collision can no longer transfer energy from one object to another. And when you can no longer transfer energy from one thing to another, then this is known as heat death, when everything is basically the same. And there's a fascinating video, I think, put out by someone called Melody Sheep, or a group called Melody Sheep, I'm not quite sure, where they look at, based upon what our current theories are in science or in physics, it projects out the next however many trillion years of the universe. And it ultimately ends with basically the universe is just a sea of particles. It's during this one, the one I'm going, all right, so what's the point of all this? If all in the end, if we're all just sort of a sea of particles. Because eventually the Earth is the sun will burn out. The particles of the Earth, the atoms in the Earth will start to drift apart. And the answer to the philosophical question is, ask Dr. Cannon, he'll know. And then, less depressing, the third law of thermodynamics. We will never reach absolute zero. I guess no system can ever reach, or a system will never reach. We will never be able to get anything down to absolute zero. Let's see, how close have we gotten though? Absolute zero, the closest that we have gotten so far is, all right, so absolute zero is negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit, or just simply 0 Kelvin or 0 Rankine. In 2000, we got it down to, in 2000, 100 picokelvin. That is 0.000000001 Kelvin. That is the coldest we've ever gotten anything. That was a piece of rhodium metal. The coldest gas in 2003 was 10 times hotter than that. So 1 nanokelvin, and that was sodium. And then the coldest molecule, so this was the gas, and then molecule, the coldest was 0.0025 Kelvin. And I didn't actually write down what the molecule was.